Hello students, and welcome to another video lecture on logic design. Digital circuits are of two types, combinational logic circuits and sequential logic circuits. In this video, we will learn about combinational logic circuits. A combinational logic circuit can be represented using this block diagram. A few things to notice about this diagram is that there are multiple inputs to a combinational circuit. Also, the circuit will have some outputs. You can have a single output or more. Also, this circuit can be implemented in AOI logic or universal logic. It is necessary to remember here that in combinational circuits, the output is totally dependent on the inputs given at a time. The combinational circuit has no memory or timing or feedback loops in their design. This is because the output is dependent at all times on the input that is given to the circuit. The process of designing a combinational circuit is also very easy. You start by writing a truth table. The truth table will help you to identify the inputs and outputs that are needed in the circuit. Next, based on the truth table, you plot the K-map. The K-map will help you to get a reduced Boolean expression required to implement the circuit. Lastly, you draw the diagram either in AOI logic or universal logic. A digital computer performs a variety of information processing tasks, among which are arithmetic operations. The most basic arithmetic operation is addition. Take for example the addition of two binary digits. We can have 0 plus 0 equals to 0, 0 plus 1 equals to 1, 1 plus 0 equals to 1, and 1 plus 1 is equal to 1, 0. The first three operations produce a sum whose length is one digit. But the fourth operation produces a sum that is made up of two digits or two bits, 1 and 0. The 1 is the carry bit and 0 is called as the sum bit. So now let us go ahead and try to implement such a circuit. A combinational circuit that will add two bits is called a half adder. Let us learn how to design it. The first step is to make a truth table. A truth table is made up of inputs and outputs. A half adder will have two bits as inputs. Let us name those two bits as A and B. Also, as seen in the previous slide, the outputs will be a sum bit and a carry bit. Let us call sum as S and let us call carry as C. When A and B are both 0, the sum is 0 and there is no carry, so we mark it as 0. When the inputs are 0 and 1, the sum is 1 and there is still no carry, so we still mark it as 0. In the same way, when the inputs are 1, 0, the sum is 1 and there is no carry, so it is marked as 0. When the inputs are both 1, in this case, sum is equal to 0 and there is a carry of 1. This completes the first step. Let us proceed with step 2 of the design process, that is draw K-maps. Since we have two input variables, we will need a two-variable K-map. We need to get an expression for sum. So let us draw a two-variable K-map for sum. We plot the values where sum is equal to 1 on the K-map. So mapping those values on the K-map, we get, obviously we cannot combine diagonal cells, so these remain as individual cells. And we get the expression as sum is equal to A bar B plus AB bar, which is nothing but A XOR B. We also need an expression for carry. So let us draw a two-variable K-map for carry. We plot the values where carry is 1 on the K-map. So mapping the values on the K-map, we get it as this. Here also it is a single cell which will remain as an individual cell, and we get the expression as carry is equal to AB. We can now go ahead and draw the diagram as follows. A combinational circuit that will add 3 bits is called a full adder. Let us learn how to design it. The first step of this process is making a truth table. A truth table is made up of inputs and outputs. A full adder will have 3 bits as inputs. Let us name those 3 bits as A, B and C. As seen in the previous slide, the outputs will be a sum bit and a carry bit. When A, B, C are 0, then the sum is also 0 and the carry is 0. Next, when you have inputs 0, 0, 1, we will get a sum of 1 and a carry of 0. Next, when the inputs are 0, 1, 0, we will get a sum of 1 and carry of 0. Next, when we have the input 0, 1, 1, we will get a sum of 0 and carry of 1. You can do this for all other input combinations. Now let us proceed with step 2 of the design process, that is draw K-maps. Since we have 3 variables, we will need a 3-variable K-map. We need to get an expression for sum. So let us draw the 3-variable K-map for sum and plot the values where sum is equal to 1 on the K-map. So mapping the values on the K-map, we get, obviously we cannot combine diagonal cells, so these remain as individual cells and we get the expression as follows. Now if we rearrange the terms slightly, for example, remove C bar common from 2 terms and remove C common from the other 2 terms, we can get the equation as follows. Now you can replace A B bar plus A bar B with A XOR B and AB plus A bar B bar with A XOR B the whole bar. This whole equation then becomes of the form A XOR B XOR C. We also need to find an expression for carry. So let us draw a 3-variable K-map for carry. We plot the values where carry is 1 on the K-map. So mapping the values on the K-map, we get it as follows. Using K-map reducing techniques, we can get 3 pairs. Let us write the values of these pairs. C is equal to AC plus BC plus AB. Remove C common to get the equation as follows. Now you know that A plus B is basically the sum from a half adder, so we can express it as A XOR B. And this is the final equation that we get for carry. Using these equations, we can draw a diagram for a full adder as follows. That's all for now. Let's learn about subtractors in the next video. Connect to the classroom for more videos and study material.